Hello, today we are going to be taking a look at how to find the powers and roots of complex numbers in polar form. First, if we're looking at multiplying two numbers in polar, the product of two numbers in polar, we have to multiply the radii and add the angles. So when we do that multiple times, for example, when we're raising something to an exponent, then repeated multiplication on the radius is going to be an exponent. Repeated addition on the angle is going to be multiplication. So that's how we end up with this formula. So if we're doing something like this example over here, where we're raising the 0.3 pi over 4 to the fourth power, we raise 3 to the fourth power and end up with 81. And we multiply pi over 4 by 4 and get pi. That's all there is to raising a complex number in polar to an exponent. Now, the inverse is going to be true mostly. We're going the other way. So for example, let's say we are finding the fourth roots of 64 pi over 2. If we're doing the inverse operations of what happens when we're raising to a power, well, let's take the fourth root of 64 and then pi over 2 divided by 4 instead of being multiplied by 4, right? We take the nth root or divide by n instead of raising to the nth power and multiplying by n. Fourth root of 64 is 4. Pi over 2 divided by 4 is pi over 8. Great. We've found the root. However, we need to look at this complex nth roots theorem. We are not going to have just one fourth root. We are going to have n nth roots. That is not a typo. That is n nth roots. That means we'll have 4 fourth roots, 5 fifth roots, 2 square roots, 3 cube roots, 10 tenth roots. This formula shows what happens. So the nth roots of r theta are the nth root of r. Okay, so our radius stays the same. Great. And then it's theta divided by n, cool, plus k times 2 pi divided by n, where k is equal to 0, 1, 2, n minus 1. Okay, let's see what this means. We are going to have 4 roots. We've got 1, we've got 2, 3, and then I did not space that well. So 1, 2, 3, and then 4. Let's do it like that. All of these, since that nth root of r does not change, all of these are going to have a radius of 4. They'll have the same 1, no matter what the radius is, positive, negative, whatever the point. Then for your angle, we are starting off with, let's erase that for a second. We always start off with that theta divided by n. So in this case, it's that pi over 8. Then we're adding some k value multiplied by 2 pi divided by n, which in this case is 2 pi over 4. And we need to multiply by k. It starts out with 0, 1, 2, goes up to n minus 1. Think about it as the same kind of number set as when we're looking at remainders, when we're dividing by a number. So this will start out with 0, this will be multiplied by 1, this by 2, and this by 3. Our first root here is going to be just that base one of 4 pi over 8 because, well, 2 pi over 4 multiplied by 0 is 0. This one is going to be 4, and then 2 pi over 4 is 4 pi over 8. So this will be 4, 5 pi over 8. This one, 2 times 2 pi over 4 is 4 pi over 4, or 8 pi over 8. So it will be 4 9 pi over 8. 9/8 pi. And then over here, we've got 6/4, which is 12/8. So it will be 4, and then 13/8 pi. So there are our 4 fourth roots. Still can feel like a lot with the k's, but let's look and see if we can find some sort of pattern here. We have 1 pi over 8, 5 pi over 8, 9 pi over 8, 13 pi over 8. All of those we are adding 4/8 pi each time, which 4/8 pi is just pi halves, which is that 2 pi divided by n, because in this case n is 4. So what I recommend is trying to understand what this is trying to say, where it's, okay, we're doing those inverse operations, we're taking the nth root, we're dividing by n, and then try and see what they're talking about with this k business here. And really what you're doing is, for all of these, they have the same radius, and then you add 2 pi divided by n to each angle. That is what that everything with k is all about. So let's do another example here and use this in plain language, the adding 2 pi divided by n to each angle, once we find this. We are trying to find the fifth roots of 16 plus 16 root 3i. Well, this is not in polar. It's in binomial. Let's get this into rectangular. So we have 16 and 16 root 3. Then we need to go from polar to rectangular. R squared equals x squared plus y squared. Now, we're going to do a cool thing here because we are trying to avoid going, well, what's 256 times 3? And then do, watch. If we rewrite this, well, let's square the 16 root 3, but leave it as 16 squared multiplied by 3. This 16 squared that's not multiplied by anything is actually multiplied by 1, right? It's our multiplicative identity. What we can do then is factor out a 16 squared, and what we're left with is 1 plus 3, which is 4. So r squared equals 16 squared multiplied by 4. So when we square root both sides, r is equal to square root of 16 squared is 16, and then the square root of 4 is 2. R is the product of those, so our R is going to be equal to 32. Then we need to find theta. Theta is our tangent inverse of y divided by x. Which this is just going to be the tangent inverse of square root of 3, which is going to be a pi over 3, but we need to look at what quadrant this binomial point is in. 16 plus 16i root 3 is in the first quadrant. That's an approximate value. So theta is just pi thirds. So this point is 32 pi thirds. Now, finding the fifth roots. Next step, we are going to take the nth root of r and then divide theta by n. Well, let's get that. We've got our, we'll have 5 different roots. We start out, our base one is, we're not looking at the cube root, we're looking at the fifth root. of 32, and then pi thirds divided by 5. Our first root is going to be, well, the fifth root of 32 is 2. Pi thirds divided by 5 is pi divided by 15. This is our, we can call it our base root. Everything else is going to be based off of this. Each time we're going to do this, add 2 pi divided by n. And we'll see why we do that in a little bit. We had 2 pi divided by n, which is 5. But to make life easy here, let's get this to have a common denominator with our base root. So we multiply the numerator and denominator by 3. So we have 6/15 pi. We set up, we're going to have 5 roots. We have 5 fifth roots, just like we'd have 6 sixth roots, 7 seventh roots, and so on. Each angle, we just need to add 6/15 pi to. So then we have 7 pi over 15, 13 pi over 15, 19 pi over 15, and then 25 pi over 15, which, if you would like, you could simplify this, factor out of 5, so you have 5/3 pi. These are our 5 fifth roots of 16 plus 16 root 3i. Why do we do what we have to do to those angles? Let's take a look at graphing these points. Right, so our 15th is going to be somewhere in here, like a little less than a 12th. The 7/15 is going to be like not quite at 1/2. The 13/15 not quite, that should be on 2. It's not quite 1. The 5/3 pi is an easy one. And then the 19/15 pi is just a little over, or a little under 5/4 pi. So if we look at these graphed out, and these are all approximates because I don't have the 15ths on the graph, if we look at this, it's almost like we've divided the entire circle into 5 different sections. 1, 2, 3, 4, 5. And each of those sections has one of these roots. The 2 pi divided by n, think about where the 2 pi comes from. We have the entire circle, the entire unit circle is 2 pi, and then divided by n, we're splitting it into n sections. So that is why we divide our 2 pi by n. So this is how we find the nth roots of a complex number in polar. Thank you for watching.